Hello everyone. My presentation is about a walking gait generation for a bike model in an asymmetric trajectory. The field of flat locomotion has proposed some fundamental models, including the spinning loaded inverted pendulums and the point mass bike. These models allow one to investigate both walking and running models. The street model remains a popular tool to investigate bipedal walking and running. This passive model, consisting of a point mass and a massless spring leg, can generate a center of mass trajectory and a ground reaction force profile similar to that of human running. The PMB consists of a point foot, a point mass as a body, and a prismatic force actuator instead of a spring on a massless leg. The PMB is perhaps the simplest mechanical model that is capable of exhibiting a broad range of gaits, including walking and running. One step of a running gait includes a stance bar, a take-off, a flight phase, and a touchdown. Stance and flight phases are continuous time phases, while take-off and touchdown are instantaneous events. In the stance bar phase, the foot is assumed to be an ideal frictionless passive pivot to the ground. Take-off is an instantaneous transition from a stance to flight phase, with no discontinuity, occurring when the vertical component of the GRF becomes zero. In flight, the robot behaves as a ballistic point mass. Due to the massless legs, there is no impact at touchdown, and so no changes occur in the robot's configuration and velocity. The touchdown state becomes the next stance phase initial condition with no discontinuity. The stance phase equation of motion for PMB using Cartesian coordinates are as the below, which is an active model without elastic elements and uses only control input FR to boost the mass. For the stance phase trajectories, we try a polynomial. Our method generates running gaits and calculates the necessary leg force profile in stance phase. The proposed method will work for any desired stance phase path profile consistent with the initial condition. We consider asymmetric polynomials with even degree. The general form of trajectory equation and its time derivatives are written as this equation. Now, the equations of motion should be solved. Taking the first and second derivative of the trajectory equation and substituting in the equation of motion, we will get the non-linear ordinary equation of x. We solved equation subject to the initial condition using the numerical code in MATLAB. The results for the ground force along with the trajectory are presented here for different asymmetries. As is obvious, the force increases by increasing the asymmetry, but the impulse, which is the area under the force curve, decreases. Here, the results for negative values of asymmetry are presented, which means that if the starting point moves to the left down, the force graph shows that the increase in the asymmetry leads to a slight increase in the maximum force, but the impulse slightly decreases. So, comparing to the previous case, when we had positive asymmetry at the beginning of the course, this case is safer because produces lower impulse and lower maximum force. If the asymmetries of x and y take different signs, the force sharply increases by time and takes much greater values than the case of asymmetry with the same sign. Although the impulse does not change enormously, the maximum force significantly increased or decreased by changing the asymmetry. Thank you for your consideration.